1 o'clock, and welcome to the Ghost Rocks Meet the SME lecture series. Today we have the privilege of having Stuart Kleven speaking to us, and he's going to talk to us about the qualification of digital X-ray systems. Before we get started, please, everyone, turn off your cameras and mute your system. It's really difficult if we start getting interrupted halfway through. So please mute your system. If you have any questions whatsoever during Stuart's presentation, you can put them in the chat box, and George and I will be monitoring that. At the end, we will be asking Stuart the questions. You can also ask questions at the end during the Q&A session. At that time, you can unmute your mic and go ahead and fire away. I know Stu is looking forward to all of your questions. So if there's any problems or with communications, just send me a text through the chat box. Otherwise, thank you for attending. And Stuart, would you please say a few words about yourself and then take it away?
Well, I've been in the NDT business this March. It's 50 years now, and they haven't thrown me away yet, so I guess I'm still doing okay. Grew up in the forging business and nuclear industry, and then eventually went to the commercial lab business and mostly aerospace to this day. Level 3 and 4 methods: penetrant mag, ultrasonics, and X-ray, and AWS CWI, and on the ASTM E7 committee for radiography, penetrant mag, and ultrasonics. So, qualification of digital systems. It's a lot of people buy equipment and then they just start using it. And if they're working to a specification, they may not realize that a lot of these specifications require qualification of the system. And it's quite complicated. So that's why I kind of threw this together. Well, anyways, qualification is somewhat complicated. This talk is going to be based on CR, computed radiography. We're working on a similar talk for DR. And basically, there are several things you have to do to start off with. First, you have to have an X-ray procedure for CR. You have to have process controls that go along with the procedure, and then personnel qualifications as well. So those are all part of the equation. Typically, there's two ways of qualifying. One is the manufacturer's method, which is the E2446. But if you're going to do it yourself, it's E2445. And that's the practice for performance and long-term stability. And this gives you all the requirements that have to be measured for a baseline and then for monitoring the system as you use it. Some of the measurements that required are contrast sensitivity, basic spatial resolution, distortion, photomultiplier tube linearity, laser jitter, laser beam scan line integrity, scan line or column dropout, and even the feeding system, slippage in feeding the phosphor plates through the system. Some of the requirements are typically, they've expressed them either as mostly of percentages. Then we have the EPS test. This develops your minimum and maximum dosage to ensure that you're getting a satisfactory image that's supplying the right information. It can be done either using the EPS E746 method, or you can use the SNR system, which is quite cumbersome. And then we have the 30-day, the plaque IQI block test. Then on top of that, not only how you obtain the image, then how you display it has to be qualified as well. So the monitor has requirements on it as well. Typically, you can't just buy a regular computer monitor down at home at Best Buy or at your Walmart. You need a higher resolution. Well, anyways, you develop this 30-day data using the SRB image, the spatial resolution of the image. Then you calculate your limits, the plus and minus 3 or 6 sigma. Then we have to do a sensitivity demonstration. So you have an X-ray tube and it has a certain power to it. Let's say you're using a 320 kV. Well, you can't shoot 3 or 4 inch thick material. So that would be outside the limits. So what you do is you take your limits and you shoot material toward the limits, either the high end or the low end, so that you can or demonstrate that you can produce the sensitivity in these materials at these thicknesses. Then there's a lot of tools involved in digital radiography, and a lot of the system performance asks that you qualify or demonstrate the ability to use all these different tools. Now, some of these are within the ASTM documents. A lot of them are in customer documents and or quote NADCAP requirements from time to time. So there's a number of different tests. So thumbnail viewing, so you can go on your monitor, look at a specific part of the image and use this magnifier to zoom in on that area. Then you can digital zoom the whole image. So you may have a certain resolution, but digital zooming, sometimes you start to lose sensitivity, you start pixelating. So again, you have to be able to recognize these things. Panning, sometimes you can grab the image if it's bigger than the screen and move it around. And you can have a magnified image and still move it around on the screen. So that's a panning tool. You can rotate the image. So that's another tool. Sometimes you'll have a long part and it's going up and down on your screen, which is perhaps the long way. But if you turn it sideways, you might be able to see other things. So again, being able to rotate the image. Adjusting, this is probably the biggest value in digital radiography, the ability to window and level. So you're able to, instead of taking 5, 6 different shots like we do in film sometimes, maybe 1 or 2 shots, and being able to window and level through different thicknesses helps you to save a lot of money that way. Histogram, again, is the window and leveling. But this is when it's in the raw image stage. And then the ROI tool, this is how you determine your pixel value and your standard deviation in the block test. So to give you an idea, here's thumbnail viewing. So here you have a big image. You can see the image, the whole screen, but there was a flaw, and I drew a box around the flaw. And then I put the magnifier just over that area so I could magnify that flaw and examine it closer rather than blowing up the whole image. So that's one of the valuable tools that they have you display. We talked about digital zoom. So you really want to know what your digital zoom is. So again, the ability to image that or display that is important. So here you can see at the bottom of my screen, it shows that this is over 200% magnified on this 214%. The ability to window and level. So here I have a casting and it's got multiple thicknesses. So on the left, you can see I'm going for the thinner areas. You can see the thinner areas. And then you get to the heavier areas with the other view. So again, the advantage of windowing and leveling. And again, you can put a series of penetrometers on there so you can display all these different thicknesses. And if you have your proper essential T-hole, you can view those areas that fall within the density or pixel values of your blocks. Other tools are a line profile function. This is kind of like drawing a line on the image, and you get all the pixels values along that line. So it's a valuable tool if your eye can't see something, but the computer can. The pixel value and digital driving level should be displayed on the image as well. Being able to make a positive and a negative image is required from time to time. And then, of course, having a calibrated measuring tool is essential as well. So to give you an idea, here's a weld, and it has a black line adjacent to the weld. And now, is that undercut? Is it mismatch in there? So I was wondering, what is that? So I drew a line across it with my profile tool. So here's the dip downward. That's the thicker section where the weld is. But you can see right next to it, there's a big spike that goes up. Here's your typical parent metal thickness. So evidently there's a thinner section right adjacent to the weld, whether it's undercut or something. But again, the eye, you can see it with the eye, but now here's a digital tool proving it out. So again, they want you to have this tool available as part of the qualification. Again, the ability to show your pixel value and your digital driving level is part of the tools that they want you to display as well. Here's the ability to capable of that should be capable, not appable, capable of negative and positive viewing. So again, the image on the left is a positive, on the right is a negative. More functionality tools capable of a one-to-one pixel mapping. And again, this is typically just a click on it, and it turns the screen to a true size. The ability to annotate on the image is important. Sometimes we make reports, and it's hard to see on an image sometimes. So an arrow or an annotation near the flaw is required. Sometimes people want to look at the digital data in the DICOM system. So we have what's known as a DICOM dump that opens all the tag information associated with that image. And then, of course, being able to go to the raw image, because again, some people feel that you can modify an image. So usually we save it as a raw image, and then you can apply your qualifying things, filters and annotations and stuff like that. So here's a typical annotation. I've listed in here FMLD, foreign material less dense, and I pointed an arrow toward that box. So you can draw boxes, you can put arrows. There are other tools as well for annotating. So again, they want you to display or just demonstrate this during qualification. More functionality tools. There are reference radiographs. For instance, if you work with aluminum, you're probably used to ASTM E2033. Well, now in the digital world, they've made those into digital reference radiographs. And basically, they mimic the E2033 images. However, every system, a lot of the different digital systems have different imaging plates that have different sensitivity levels. So some are at 80 microns, 160 microns. So you have to enter the reference images when you load them into your system at the proper value. So the ASTM reference images have these capabilities listed as you're putting them into your system. So for instance, we have two different style plates, the ST6 and UR1 plate. Now, once you enter these, you'll have the image of the part, and then you'll have the reference images as you split your screen. they have to be able to move together. So they have to magnify together, and they have to change brightness and contrast together. So here's a typical split screen. So as I magnify the item on the left, the reference images on the right have to magnify at the same rate. If I change the brightness and contrast on the left, my reference images would have to do the same on the right as well. So again, this is part of the demonstration that normalization has taken place in this system. Part of the qualification is listing all your equipment, and they're very specific on that. So your X-ray cabinet and dimensions, your source to object distance, your tube manufacturer, all the details, even the serial numbers, workstations, model numbers, serial number, bit depth, your monitor, the model, serial number, megapixels, and then what version of the software you're using on each of these items. So again, this is all part of the qualification. So let's say you buy a new X-ray tube. Well, that's a major part of the system. So that would require a requalification. So that's why each item is listed in the system qualification. So imaging plates, again, we identify each type of imaging plate and what type of cassettes. You have to identify the type of cassettes you're using as well. You're using the manufacturer's hard cassettes that automatically scan, allow the plate to be scanned, or if you use a flexible cassette and then transfer it to the hard cassette to process. So you identify all of those as part of your system qualification. Now, some of the specifications, again, this would be more customer driven. It's typically optional, but first of all, you have to identify certain plates set aside for qualification, and you don't use these for production. You only use them for your quarterly long-term stability test and process controls. That way they're not beat out and worn out and used every day, so that you're getting the same kind of test results all the time. Then there's an optional test. Some customers and some specifications say, check every plate and take the percentage variation and compare it to all other plates that you have, and they all have to be within a certain percentage. So again, this is an optional test. Your photometer for checking your brightness on your monitor, you have to identify the type of sensors you're using, your photometer, and what kind of measurements you're taking. Is it foot candles, foot Lamberts, candelas per square meter, or whatever units you're using? Now, it's one thing to shoot an image, but now you have to qualify it. Again, there are IQIs that we use in production. We use the duplex wire gauge, the ASTM 2002. We use the Phantom for qualification for your long-term stability. We use regular standard IQIs. We use the EPS plates in the 746 document. And then, of course, you've got shim blocks and different materials that you might be testing. So here's a typical E2445 Phantom. It has different features embedded in it. It's got a laser jitter T. It's got contrast blocks and different materials. It's got uniformity checks. It's got bands for checking slippage and banding. It's got distortion, so you can have measurements in two directions and calibrate that way. And you have your E2002 gauges. Now, there are different styles of Phantoms, and typically you need nowadays two at 45 degrees to each, or 90 degrees to each other, with a little bit of movement. I think it's 5 degrees offset. So we had to tape an extra set. We bought one of the originals way back, and then we had to add an extra set of a line pair gauge. So let me go back. So here are your contrast gauges. So you got 4, 3, 2, and 1% contrast sensitivity. So if you view that block, this one happens to be in stainless steel. You can see that we've imaged 4, 3, 2. I can just see the 1% block, the step in there. So that would qualify you down to 1%. Did I say E2002? This is E1647. This is a black line test. If you shoot electron beam welded parts or aerospace parts looking for cracks, they limit the angle that you're allowed to shoot. And typically it's very close. So you have to do a black line test. So we put 2 blocks side by side against each other, and we try and show a black line to show that we have the angle close enough that we'd be able to see voids in an EB weld. Since plates are used over and over, you want to make sure that your erasure is working. If you get ghost images on your plate, it's going to interfere with further x-rays that you're taking. So you want to make sure that your erasure system in your CR system is working. So typically you cover half of it, you expose it, and then you do a check, and it has to be less than 2%. Once you erase it, the covered side against the side that was exposed has to be less than 2% pixel value. That way you know your erasure system is working. You also have your SRB, your detector spatial resolution. And again, this is displayed with the E2002 line pair gauges. So you draw a profile line. You can see we've drawn a profile line. And there are certain requirements as to the width and number of pixels in that line. And then you draw it along the length of your gauge. And you get an image like this. And down to a certain point where you see 20% difference, that's your limit. And I believe you're allowed 1 more line pair after that. Your daily plaque wire test is shot every day. And again, this is compared against your baseline. So you do a ROI and you get your standard deviation and you record that every day. Now, your dose has to be qualified. So we use the EPS. You can use the SNR. As I mentioned, it's quite a bit more cumbersome. It takes a lot longer. And basically, we use these E746 panels with holes drilled in them. You use a number of radiographers to view them, and they each come up with a certain amount of holes that they identify, and then you do an averaging. And you do it with different doses. And then you come up with what's known as a plateau. So basically, this is the range of qualification of your pixel values. So at the low end, we're qualified down to 395 pixels. And at the high end, 3,569. So again, after the ends, you'd run off the ends of this, you're not getting values on your EPS plates. So this is your qualification. So as you're doing images and you look at your image on the bottom, as we showed down in the corner on your image, if your pixel value falls outside your plateau, then it's not qualified. So we document our baseline, your 30 days, and then your standard deviation each day, your CNR, your basic spatial resolution. Some of the other process controls or long-term stability, banding. So again, on the banding strip, you're allowed a plus and minus 15% max pixel value. So again, you draw a line on there or a ROI box and you get your numbers. And if it's less than 15%, there's no banding. Laser jitter, as your plate is feeding through the system, if it's not moving at the right rate, it might jitter or shake, and that will produce a distorted image. So you look at the edge of the laser scan of this T, and it'll give you the image in both directions, in the feeding direction and in the cross direction. And now I've never seen any bad laser jitter, so I had to steal this out of an ASTM document. So here you can see this shaking. So it would distort the edge of the T and you'd have sawtooth marks like this on your image. So that would be a problem with laser jitter. Uniformity. So you take a reading. In the end, there are three little blocks or bullets in the end of the phantom. You take your reading in the middle and then the two outer ones. And again, they have to be within plus and minus 15% of that center spot in pixel value. Your photo multiplier tube can cause problems too. So here you can see a problem with nonlinearity. You see this fade line or difference here. So that would be a problem. So that would either need adjustment of the photo multiplier tube or perhaps there's something faulty there. Scanner slippage. So again, you take a measurement, and again, if there's any slippage, you'll see lines across it. You draw a profile line and you'll see a change. Scan column dropout. This is when the laser fails to read an entire line of data. So you would get like a white line on your image. And that would be, again, a problem. Missing data. Again, if you're going to do any kind of measurement on your system, if you have flaws and you want to measure the, let's say, the pore size or maybe the area of some shrinkage and compare it against the reference radiographs, again, you got to be able to measure accurately. So again, calibration in two directions using these measuring tools that are built into the phantom. Monitors typically have to be checked, and there's a daily and weekly checks. So again, you got your calibrated photometer. Some of the tests they require: brightness, contrast, resolution, high resolution, low resolution, no flicker. Your monitor isn't flashing as you're looking at it, and then the contrast. So to do this test, you use what's known as a SMPTE pattern, Society for Motion Pictures and Television, developed a long time ago, but it works. And basically you have your high contrast and low contrast lines in different areas. I number them 1 and 2. And then you have your a high end. There's a gray block inside of a white background, and here you have a lighter gray block inside of a black background. So those are two checks. And then finally you measure your at 5 and at 4. This should be totally black, and this should have a white value. You get your contrast ratio off of that. So here, looking at those corners, let me go back again. Looking at your corners, either low contrast or high contrast, you want to make sure there's no aliasing or data missing. You can see how these are split. Again, all the different requirements. all the different tests. Again, these blocks, you have to see that 5% signal on a 95% back, let's see, 5% change superimposed at a 0, and then the other one is the opposite. And then finally your brightness and that you record. Qualification of the system, again, I mentioned different materials that we use, so you have to qualify the limits. So here's some tests in different materials and some of the different values you get for certain times, exposure, and what type of, here we happen to use vinyl cassettes and different plates. So here's our, like a total report. Then you start to log all the test results of your qualification with basically the requirement, our baseline value that we got, and then the requirement here. And of course, your monitor as well down below. Finally, you need a qualification statement from the manufacturer. It's called a daunting conformance statement, and that's part of the qualification data. And what that does is it tells that your system can share with other people's systems and see the same type of data. And of course, they're going through a lot of round robin work in ASTM right now and verifying the use of daunting and qualification between different systems and interoperability. So that kind of is the whole system put together that we've done on our systems. And that's all I have to say. Back to you, Karen. Also, Karen, if anybody has any comments as to presentation requirements, you know, like if they want to see more or they didn't understand one of the images, it didn't look good, let me know. You know, any kind of feedback as to the presentation.
Okay, send any and all feedback to me and I will make sure that Stu gets it and connect you to be able to discuss it with him personally. And without any further ado, if there's nothing else, George, have you got anything else to add?
That's it. So that was a great presentation. Thank you, Stu.
Okay, thanks, George.
Thank you all for joining us and look forward to more future talks. Thank you and have a great day.
Thanks, Karen.
Bye.
Bye-bye.